Hi, good evening.
Good evening.
Hi.
How's it going?
Hey, Stuart.
Hey, Deb.
Here's Gwen. Hi.
Hi, Gwen.
Hi, Stuart.
Hi, Deb. Hi, Ryan.
Hello. All
Hi,
right.
Ryan.
Welcome.
Where's Joanne?
She's in Minnesota, so she's not joining tonight.
Oh. Where's Adrian?
She's doing Shakespeare downtown.
Is she in the play?
No, she's watching it.
Watching it. Is it on tonight?
Yeah.
Not the show in town.
I thought the one in town, she said.
Oh, well, good for her. Much Ado About Nothing. I love that show. I love that play.
Good.
You're
So,
not
Ryan, last one, right?
That's right. Yes. Today is the last sci-fi explained for the foreseeable future. If it turns out I have free time while the school year is going on, I'll hopefully bring it back. But for now, yep, this is our final meeting.
So what did so Sam is not going to do something else?
I'm not sure what Sam's plans are because I feel like he has a lot on his plate and he keeps adding to it.
Yeah.
Right now he has the Cosmos show once a week.
On Tuesday.
Yeah, I saw it. We saw it last night.
Right. Yeah, so that seems to be going well for now. And
Yeah.
I think if that's the extent of our public programming virtually, then that's great. I think it's phenomenal.
Yeah.
So it's always nice to just have a variety and switch it up.
Sure. He did. I don't know that he announces to the public, to the watching public, but he seems to involve some sci-fi movie with the Cosmos Night.
Yeah, it has a little bit of sci-fi explained in there for a bit. So I think he spends 10 or 15 minutes going over one of the movies that we've covered. So I think, I don't remember what last night was, but
Gravity.
Okay, yeah, Gravity.
But it isn't like he gives you a heads up to refresh your memory.
I see, yeah. Maybe I'll ask him about that because he's always looking for suggestions.
Yeah, I sent him what happened is I looked at an older show and saw that he was doing that. So I sent him an email, but no response. So whatever. Okay. And Tuesday night is not good for me because I have geology twice a month.
Okay.
But he didn't know that before. So now he does. So whatever. Okay. Anyway, tonight, you.
Yes. Let me pull up the slideshow here. The Wandering Earth. And yeah, I didn't realize this is only available in 3 languages other than English, but then you would remind me it was dubbed in English, so I made it work.
Yeah.
And so we're talking about the sun engulfing the earth, which we should expect to happen in a few billion years. And, you know, this population of the earth decided that we need to move the entire planet away from the sun. And we're going to just see how feasible that really is.
How feasible is that? Yes.
Yeah, let's start with that. They had built fusion-powered propellers to move the Earth through space. And I think we had discussed fusion on another episode a while back, probably several months ago now.
Yeah.
It doesn't look like fusion has been mastered yet.
They're working on it. They have some huge magnet thing going on somewhere.
Right. And we'll start with just how does it happen in the sun? Because the sun, the only way it shines is through fusion. And the sun is extremely massive, extremely hot, and can generate enormous temperatures and pressures. And we think, oh, that should be sufficient to fuse protons together to form helium. But in another meeting, I had said, actually, you need a lot more energy to fuse protons. 27 million degrees Fahrenheit actually isn't even enough. And so we need to thank quantum tunneling for the sun's energy. The only way that protons are able to fuse to each other is through quantum mechanics. And so it's not just the protons are physically being smashed together. There's an uncertainty principle. And we say that since protons are subatomic particles, they have a probability of being in a spot that we didn't predict. And they sort of overlap and overcome that repulsion because protons are both positively charged. Classically, they would repel. But there is a minute, minuscule, extremely small probability that the protons are actually closer than they should be, because we can't guarantee their precise position. And even though it's a very rare probability, it's a very small probability that this happens, there is an abundance of protons in the sun that this happens regularly. And protons quantum tunnel all the time in the sun's core. And then we have fusion, and they're able to combine. So in order to do this on Earth, we would need to really take advantage of this uncertainty principle and perhaps fire protons at each other, quadrillions of times a second or something, and hope that, oh, we have one of them fused together.
Can you just explain the quantum tunneling aspect
Yes.
a little bit more?
Mhm. So I'm trying to find a diagram.
Yeah, I remember you had this last month.
Yes.
Okay. Here's basically an actual tunnel, if you will, going under this line here. So they're supposed to repel. Protons are supposed to fly away from each other if they get too close. But it's not as simple as proton being exactly in this spot and another proton being exactly in this spot. It's an uncertainty. There's a hazy area. It's a little gray where the protons are. We say the proton is probably in this vicinity, and the other proton is probably in this vicinity. And these two blurry circles you can imagine as distributions, probability clouds. In the very center, you have maybe a 99.9999% and like a lot of nines. We're talking 1 in 10 to the 28, as this diagram shows.
Which diagram are we on?
These are the probabilities,
Yeah.
and that in that white space is that not the chance of them being there. The uncertainty principle is
Yeah.
99 point.
Yeah.
So it's almost certain that the proton is in the center of this blurry bubble. But there is an infinitesimal probability that it lies on the edge here. But it's not zero. And so these protons can actually get closer than they're supposed to. And that's the weirdness of quantum mechanics. At a certain point, protons are supposed to repel. At a certain distance, they have to go away from each other. But there is a very small probability that they get close enough to fuse. And that's what this green area is.
What does
Fusion
that mean?
happens.
The Coulomb barrier.
The Coulomb barrier is sort of that repulsive force, the Coulomb force, electrostatic. Just like gravity, the gravitational force, we say electrostatics is the Coulomb force. So this little caption says, is the sun hot enough for fusion? And technically, no, not really.
Is this the, there's electromagnetic force, gravitational force, Then there's the weak and the strong force.
Correct.
And is this the weak force?
This is the electrostatic force. The
That's different-
electrostatic
Yeah.
is preventing these protons from touching.
So is
Usually.
electrostatic different than the electromagnetic?
They're the same thing. Electromagnetism are two sides of the same coin. Electricity and magnetism are related.
So there's nothing here with the weak force and the strong force.
No, that is within the atom itself and within the nucleus itself.
Mhm.
That's when you experience those weak and strong forces.
Yeah, because I thought with these protons being so close together, you're going to maybe have those weak or strong forces.
Yeah.
How about to the diagram that's just adjacent to the, that's showing you what happens actually with the protons breaking down in order to join and create I mean, I'm
Oh.
pointing, but yeah, exactly. The top left.
Proton-proton chain. Yes.
Yeah.
So
That
it's
was a
not
thought.
just, right. So it's
Strong
not as
reasoning.
simple as two protons come together and we have helium. There
You
needs to
need
be
you need
two
neutrons.
pairs. You need two pairs of protons to collide. And then you have a reaction where we have a positron that's sort of like a positively charged electron and a neutrino released, as well as we have now a neutron because it lost the charge from the positron and then goes down the chain. So I can just explain going top down. We have two pairs of protons. They fuse and release a positron and neutrino. And what we're left with, the product, is a neutron and a proton. That now has to join with another proton that we haven't even encountered yet. They come together and form helium-3. And then the other, the same exact thing happens elsewhere. And then we have two helium-3 atoms. They come together and form helium. And then you also have some excess here, two excess hydrogens.
So I see you have hydrogen 1 and hydrogen 2. Didn't I read somewhere that the kind of the ratio of hydrogen 1 to hydrogen 2 tells you how far a star is in terms of its burn life?
Yes, that's a good point. We can tell the star's age by measuring the ratio of hydrogen 2 to hydrogen 1. So it's like, what's the fuel ratio? And that's like a more precise measurement. Normally we would say, what's the ratio of just hydrogen to helium? And we say, okay, if there's more helium, it's older. If there's more hydrogen, it's younger, for the most part.
Interesting.
Yeah, and to go back to your other point about the strong and weak nuclear forces, the strong force is what's responsible for joining protons to, no, actually, no, it might be the quarks. Let me, hold on. Those are gluons.
Mm-hmm.
I think the strong nuclear force is what's binding, hold on. Let me get this right. Yeah, they bind the quarks. So this is, if you cut open a proton and look inside of it, you have 3 quarks in it. So that's like within the proton itself, we see the strong force.
What about the weak?
And then the weak force is like thinking of radioactive decay.
Mhm. So if you have,
radiation like that.
if you have photons, gravitons, and gluons, what is the particle in the weak force called?
It's called a, I think a W and Z boson.
Hmm. Now we're moving into bosons, and Higgs is not far away.
Right.
Good.
Yeah, so photon does the electrostatic force. W and Z bosons do the weak force. Gluon does the strong force. And then potentially a graviton would mediate the gravitational force, but we haven't found it yet, if it even exists at all.
Have we found gluons?
I think so. Let me see what if they're even stable. Yes, discovered in 1978 and 79. I wonder how long they last, though.
Yeah, because the Higgs boson only lasts like 1 to the 10 to the minus 22nd seconds.
Yeah, which is crazy. Oops. They're kind of like photons almost,
Mhm.
whereas they don't really have much mass. And they are completely stable, in fact. Gluons are completely stable. It's hard to think of photons as particles. It's packets of energy.
Be careful, or I'll shoot my gluon beam at you.
Yeah. And the other thing I wanted to, just get a realistic perspective. If we were to try to move the entire planet,
Mhm.
Earth is pretty heavy. And of course, we can't weigh the Earth because there's no table to put it on to exert a force. But we can estimate, given the Earth's density and given the Earth's radius and how it's a little more dense at the core than at the crust, we say the Earth is probably around 6 times 10 to the 24 kilograms. So that's 6 septillion kilograms. And looking at the article here, they installed 12,000 engines just on the northern hemisphere to give it some torque. And also along the equator. But if you do that, you're going to unleash some pretty nasty natural disasters like earthquakes and tsunamis and landslides, probably. So that's another thing that we would need to mitigate.
Well, they were talking, well, the first thing is they had to stop the Earth from rotating.
Mhm.
I mean, I suppose because they only have, one set of 10,000 engines in one place for propulsion, right?
Right.
Otherwise you'd have to have them all over the globe firing in sequence as the Earth turned.
Mhm.
But the other issue about earthquakes that came up as they approached Jupiter is they were approaching the Roche limit.
Yes. And I'm not sure if I had touched on this once before, but
Yeah.
the Roche limit is what
Yeah.
happens when things that are orbiting around a planet tend to break up because of tidal forces. And this is what's going to happen to Mars's moons. So Mars has 2 moons,
Yep.
Deimos and Phobos, and they are slowly coming closer to Mars. They're encroaching on the planet, and there is going to be a point where they reach the Roche limit, And at that point, they're either going to disintegrate and form nice rings around Mars, or they're just going to come flying into the planet and crash land.
When's that going to happen?
I think maybe in a million or so years.
So pretty soon,
Yeah.
as time goes.
Yeah.
But I'm thinking, remember Shoemaker-Levy? You wouldn't.
I do
You
recall,
might.
yes.
Yeah. Stuart, do you remember Shoemaker-Levy,
Yeah.
the comet that broke up as it hit Jupiter?
Yeah.
Yeah. So that was sort of the same phenomenon.
Mhm. Yeah, 25
sort of.
million years. 20 to 70 million years from now.
A lot
Mars-
longer than when the next Yellowstone caldera is going to erupt.
Yeah, that's true. So, yeah, this is what happens when you reach the Roche limit. Tidal forces will kind of rip you apart.
Interesting.
And it'll happen to our moon as it approaches us.
Well, we actually have a different scenario because our moon is actually receding from Earth. So our moon is on its way out. It's slowly drifting away from us.
Oh.
What was the closest the moon? Well, we went through this once. The formation of the moon.
That's right.
Formed when something hit Earth, right? It was a proto planet, and but then the moon stabilized. I guess it's 250,000 miles now, but you're saying like a billion years ago, it might have been 125,000 miles from Earth. Or something?
Perhaps, yeah. So it was an impact. Theia was the name of the planet. So we originally had 9 planets going around the sun, and then Pluto. So if you want to count Pluto as a planet back then, 10. But yeah, Theia was another planet, crashed into Earth and ejected lots of the planet's material into orbit. And then it coalesced into the moon fairly quickly. It only took maybe 10 days for it to form its moon. Yeah, it was incredibly rapid. And back then, a day on Earth was something like 12 hours.
Mm-hmm.
It was much less than it is today. And slowly, the moon slowed down the Earth's rotation because of that tidal force. Tidal forces are all around in the solar system. So the moon was tugging on the Earth, it was slowing it down. And at the same time, the moon is receding away a few centimeters every year.
Which adds up, I guess, over a billion years.
So why?
Why is the moon receding?
Yes.
It's just
Orbital mechanics.
I was just going to say orbital mechanics. Yes, it's sort of you just throw a bunch of rocks into orbit, things are going to happen. Some things are going to fly one way, some things are going to fly another, and we always are conserving angular momentum. That's always going to be conserved, no matter where you are in the solar system or how fast you're moving. The reason planets are in a disk is that conservation of angular momentum, because there was a preferred direction. If you were to take the average of all that spinning matter when the solar system was first formed, there was one direction that was moving faster than any other direction. And then everything just sort of conformed to that plane. And that's why the solar system is more or less a giant record player.
You know, in that book, that physics book that came out that I was telling you guys about that I read, and he was building up, 10 key, I think it was called Fundamentals, 10 Key Elements of Reality.
Mm.
But it was very clear that there was one point in there where I had to understand a lot more about angular momentum than I did, and I still do, because I just haven't had time to really think about it. But you sounds like you do, that you've learned about that in school, because it sounds like it's very important in building up our current model of physics and reality.
Of course, yeah, definitely.
And I never really focused on it that much.
Mm-hmm. And I did most of my work with orbital mechanics, not even in a space course. It wasn't even devoted to space. It was more of a math and physics course.
Mm-hmm.
Just, free body diagrams and what was it called? The three body problem, where you're having multiple objects.
Is angular momentum important in GPS?
Kind of, only if you're trying to figure out the speed at which the satellite itself is moving. But the way you're able to know your location is more like geometry.
Mm-hmm.
It's taking at least 3 satellites and pinpointing your X, Y, and Z coordinate. So for instance, if I were to give you a 3D grid or a box, I would only need 3 bits of information to tell exactly where you are in space. And I guess you could also argue there's a 4th dimension, time. But if instantaneously you want to know your position, you just need 3 coordinates: your height, your
Mm-hmm.
latitude and longitude.
Mm-hmm. It's interesting.
It came up in discussion of some other movie that you couldn't know where you were out in space because you didn't
Right.
have a GPS system.
Mm-hmm.
And no reference point. Yeah.
You don't have, but say you're focusing, on whatever, on Aldebaran. Can't you use that as a reference point for direction? Though you may not have
You asked the same question exactly when we were doing this last month. It's a good question.
Did I? Because I don't remember asking it. I just remember thinking it. But okay.
Right. Yeah, it's kind of a tricky question to answer, because here on Earth, even if we remove the planet and we're just like floating where the Earth used to be, we can still have a celestial sphere around us and use the constellations to figure out where the North Pole should have been and so on. But if you wanted to use that to get to Mars, it would be a lot more complicated. If you, let's say, didn't have it in your immediate sight, because the stars are so far away.
But they're moving relatively slowly with respect to each other, no matter what their 3-dimensional distance.
Mm-hmm.
So
I'm trying to think now, because, all right, let's say you wanted to travel to Polaris.
yeah.
And you could just look up and see the star and hopefully travel in a straight line to it. But if there was anything on the way, you have to remember that thing is also moving. Everything in space is moving. There's no such thing as being stationary, because the stars themselves are orbiting the galaxy. So by the time you get to wherever you're aiming, you're going to be way off course. So you would really need to use gravity as your navigation device. And that's only big. Now, if you froze the solar system and you froze the stars in the whole universe and they just were still and you floated there, then I think it would be a little more easy to navigate. Then I think you could travel from point A to point B with fewer issues. It's so dark.
Yeah.
Can I go back to one other point before we move on?
Yeah.
So this is what I was reading and got me thinking before. It says, I'll just read you a couple sentences. Conservation of angular momentum requires that even the direction is conserved. A simple example is the gyroscope. Then it says spacecraft have inertial guidance systems, I guess, in addition to GPS, and early inertial guidance systems use spinning gyroscopes. So that's not the GPS system. Inertial guidance systems, which are different, I guess.
Yeah. So if you're in a plane, for instance, or a fighter jet, you're going to have, I mean, you're moving at such great speed and with such great acceleration that it's important to know how you're moving in addition to where you're going, where you're headed towards.
And that's inertial guidance systems.
Yeah, because like, yeah, it's great. Let's say you're heading to the nearest airport, but it's not so great if your plane is upside down. You know, that's a different story. So pilots want to be aware of, okay, what's up and what's down, not necessarily what's north and what's south.
Got it. And I wanted to just talk about one other thing. When we were talking about the mass of the Earth and moving it, it reminded me of, I was reading about, about white dwarfs, I think, are not that much bigger than Earth, but their mass is exponentially more. And I guess neutron stars are
They're
much
smaller
than Earth, right?
Oh, yeah.
And their mass is exponentially more. I think we've talked about this before.
Yeah, white dwarfs are really planet-sized, and neutron stars are city-sized. And so, yeah, they're one of the most dense objects in the universe.
So are neutron stars so dense that protons and electrons have fused in essence?
I don't. That may be how
Go ahead.
Yeah, that may be how they're formed, because I know you can like create neutrons. And it's kind of a tricky process. I'm not even 100% sure how it is, but neutron stars themselves are just a ball of neutrons. And
So how do you get that?
Yeah, I think you're right. I'm not 100% sure, but it probably is like the electrons and protons coming together. Yes, every proton and electron gets crushed into a neutron. That is correct.
But it would take that density, I don't know how to put it, but that tendency to density to crush them together.
That's all gravity. Gravity is crushing it.
And I guess the difference has something to do with size, about whether it ends up as a white dwarf or a neutron.
That's right. A really massive star, 10 times larger than our sun, will explode into a supernova. And what you'll be left with will either be a neutron star or a black hole. Whereas a star like our sun, much less massive, you'll be left with the white dwarf.
And apparently there's things that haven't had time to even form yet, like black dwarfs.
Yeah,
The
right.
universe has to be much older.
Yeah, black dwarfs, the
blue
universe
dwarfs.
itself is too young for them to even exist yet. And then, so yeah, speaking about stars and life cycles, we keep talking about the sun's going to eventually engulf the earth in a few billion years. But how does this happen? And we kind of brushed on it a little bit. Stars eventually run out of fuel. They don't have enough hydrogen left to fuse into helium. And so as a last ditch resort, the sun will start fusing helium, and helium will fuse into carbon, I think. Yeah. And then once it's got a carbon core, there's no more energy left. The sun won't have enough energy to fuse two carbon atoms together. They're just too heavy, and the sun's not hot enough. It's not dense enough to fuse those carbon atoms together. And so what happens? The outer layers start expanding. And it cools off. So yeah, it's going to get enormous if you take a look at this diagram here. And I'm trying to figure out just why the outer envelope expands. I think it's because all that fuel is being pushed outward as it's being expended, and it grows and gets a lot less dense and cools off a bit.
But you can have fusion up to the point of iron, but we're just not hot enough and big enough.
That's correct. A really massive star won't be able to fuse to iron. Something like Betelgeuse.
Well, they talk about something. I've heard the concept of an iron star.
Yeah, iron core.
Well,
essentially.
Is that what an iron star is?
Probably. I think that's what they're referring to.
I think you're talking about Spielberg.
I'm actually thinking about something real that maybe like a black star hasn't had time to.
Oh, hypothetical type of star. Okay.
Yeah.
Compact star. Oh, look how far into the future.
Yeah. Pretty far. We're not going to be around.
1500. Geez. Oh, quantum tunneling. Cold fusion. So hypothetically, because I guess it wouldn't be physically impossible, ordinary matter could fuse into iron 56, which is kind of nuts to think about. That's so crazy.
What's the usual, the common isotope of iron? I have 55 point something on my map, on my periodic table here.
Yeah, iron 56 is it. About 92%.
Well, iron 56.
Mm-hmm. And here's the reason why we can't fuse elements heavier than iron. This is your cost benefit analysis, I guess, of different elements, of all the elements actually. So you start with hydrogen, and you don't need that much to fuse to get some energy. You get like 1 mega electron volt for 2 hydrogens.
More than we can do on Earth right now. Right?
Oh yeah, so this is a pretty good deal. 1 mega electron volt for 2 hydrogens. But then when you start fusing helium together, for just 4 nucleons, you get 7 mega electron volts. So that's a really good deal. And then the highest possible energy you can get from any element is iron. Iron 56, you get close to 9 mega electron volts of energy. But anything after that, the energy required to fuse would be greater than what you get out of it. So at this point, riding down the peak, every time you fuse atoms together, you're going to lose energy. It's going to cost you energy to put these atoms together because they're so heavy now. But what you can do is split the atom, and then we have uranium at the end. If we, this is called fission. If we split uranium, then we get energy. So now, after iron, it's a better bet to split the atom rather than fuse it.
So is that, I mean, was that our initial atomic bombs?
Yeah. Uranium, you get a ton of energy out. And I think, what's it called? Energy density. Just, I love looking at this. A list of the energy densities of things. So gasoline, looking at megajoules per liter. So basically how much energy you get out per liter of gasoline. And this is what we use to basically power the world. 34 megajoules. Not that bad. And that's why it's our fuel of choice for automobiles and such. 34 megajoules. If you look at uranium, megajoules per liter, we get 1.5 billion. So nuclear energy is far more powerful.
That's an interesting chart. Never saw that one before.
And then we can get some enormous potential from fusing hydrogen. But we don't think we're there yet. What's TNT? I'm just curious.
Trinitral toluene?
Yeah.
Oh, yeah.
We've never done fusion on this planet, right?
Nope.
Humans.
TNT. I don't
It was
think
at the bottom. It was the very bottom.
Yeah, not even that much. For some reason not listed, but I guess it's around 1,000.
It was down there. It was like 4,000
It was the second from the end.
TNT.
But it didn't have an energy density.
Look at the very bottom and up one.
Yeah, a 4.18
Oh, it's 4 point, not
megajoule. Oh,
4,000.
so that's per kilogram. That's why, because TNT isn't like a liquid. So, it'd be like.
So
10 times.
how about Earth's oxygen fueling an explosion of Jupiter, which is 90% hydrogen, right? Seems a little.
Oh, so
In
yeah,
the
hydrogen
movie.
reacting with oxygen.
Yeah, we don't have enough oxygen, do we?
Yeah, our atmosphere is what, like 20%?
Yeah.
Is that what they had in the movie?
Yeah, that was the movie thing. That's how they were going to gain propulsion. You know, instead of ejecting the warp core, they were going to have the Earth's oxygen atmosphere with Jupiter's hydrogen and an explosion to trigger an explosion to be a propulsive way to get Earth away from crashing into Jupiter.
Wasn't
That's
that from
the
the
movie.
space station going into and blowing
That
itself up? And
was the ignition.
Mhm.
They needed they needed fire to ignite the
Got it.
bigger explosion. Yeah.
Oh, I see.
So they used the guy had the bottle of vodka
Mhm.
that the
Mhm.
Russians snuck in.
Mhm.
I mean, really, what the hell?
Almost gonna die.
Terrible movie, but a lot of interesting concepts.
Mhm.
Well, you know, the guy that wrote this, the novella that this movie was based on, is the guy that's
Uh,
written the best sci-fi trilogy I've ever read.
which is what?
Well, the Three Body Problem is the first one. I can never. Adrian says I butcher his name, so we just refer to him as the Chinese guy. But it says it's based on a novella by somebody.
Yeah, it does, but
What was the name of that?
Liu Cixin is the.
what's the name of the book?
I think it's a novella, short story. Maybe it's called the same thing. Is that it?
What's it called?
It might be The Wandering Earth. I don't know. The novella. It says it at the beginning of the Wikipedia thing.
When's
2000, 2000 novella, The Wandering Earth. Yeah, right. This guy,
Mhm.
the Chinese guy. And the film, it's incredible that it grossed 700 million.
I was going to say
Northwest-
fifth highest of all time.
Well, it's the fourth highest, I think, in China.
well,
Fifth
it's China, you know, you get, you know, one block of people in the city and you got it made.
highest.
Right.
But Gwen's son is fluent in Chinese.
And so kind of the last point I wanted to bring up was, can we even survive without a sun? Let's say we were to just
Just if you need
propel
some-
ourselves away from the sun and just enter interstellar space. It's going to get quite cold, close to absolute zero. And luckily, we should still have a magnetic field and an atmosphere.
Well, what if the Earth is not spinning? Would we
the Earth is-
have a magnetic, and how do you stop the inner parts of the Earth from spinning? But would we have a magnetic field?
That's a good point. Yeah, because like let's say we were to stop the rotation of the Earth, I feel like the insides would still be swirling around because of their inertia.
But
Like the
that-
mantle is circulating.
Right. Well, how do you stop the outside of the Earth without stopping the inside of the Earth?
I think if you think of it like a layer cake, and the layers can slide over each other, the core may still be able to, let's say, gyrate, and the crust kind of just sits on top of it. But even then, I feel like conservation of angular momentum, something has got to give. So you're thrusting your engines outward, like in the opposing direction of the Earth's rotation.
You know, there's a lot of discussion about what makes tectonic plates move.
Right.
And one of them has to do with the circulation of the mantle. So if you stop the crust but not the mantle, I think you'd have a mess.
Yeah, that's a good point. I don't even think the engines would be a practical idea. What I think would happen is if you were, let's say, engage all those engines at once, you might like rip apart the crust and that's it. And you'd cause like catastrophic earthquakes.
Yeah,
Probably wouldn't
tsunami's the
slow
least
Earth
of it.
down much at all.
Yeah. But I don't think you could really stop the Earth without stopping the innards.
Right.
And then what do you
Yeah, it's
have
a good
left
question.
when you when you're trying to put it in another solar system, how is that planet even? That's what didn't make sense to me. If you've lost, eventually you would lose the EM field, right? What's left
Yeah.
of this
So let's say
planet that
convection
you have all
stops.
these people on?
Right. So that was sort of like what I was thinking. Let's say we lose we lose our magnetic field. We don't have any shield from radiation. How are we going to keep ourselves warm? And, assuming convection stops, let's say there's no more convection going on, we still have radioactive decay. And that's what's a big component of keeping the inside of the Earth warm, is we have radioactive decay. And also differentiation. Less dense rocks are floating to the surface and pushing out more dense rocks and that are sinking. And this cycle kind of can generate a little bit of heat for us. So if you were to dig deep into the Earth, you could probably still stay warm. But then
Would it last for how many years did they say you need to get to the next star?
2,500.
2,500.
Mm-hmm. Yeah, I don't know how
Alpha
long you could.
Centauri.
I don't know how long you could subsist on the residual interior heat. But then you ask, what about photosynthesis? If we have no sun, how are we going to have food to grow? How are we going to eat? And my thing would be, you have plants deep in the ocean that never receive sunlight, organisms down there, and they may be able to survive indefinitely without a sun, because there are plenty of organisms. In fact, the majority of organisms on this planet probably have never ever seen the sun.
But it was plants like cyanobacteria that created the oxygen that we live on. Now, you don't need oxygen. You can be, sulfur dependent instead of oxygen dependent, but it won't be us.
Yeah.
Coming out the other side. Is that what you're saying? We will convert ourselves to adapt to.
Well, we'll be something else.
Right.
Maybe, yeah.
And life without an atmosphere, you become just a rock like Mercury, and you need the magnetic field.
Yeah, well, to be fair,
to protect the atmosphere, right?
Yeah, the very early Earth, I don't think had very much of an atmosphere either. It was kind of just a hellacious place to live.
Indeed, it was called the Hadean Age. Yes.
Yeah. So
everything would have to start over, even though
I think it's like hitting the reset button. I agree. Yeah.
Yeah.
So that could be billions of years on top of it.
Mm-hmm.
On top of the 2,500 years. Now you get there. Now you have to. Just seems easier to go to another planet in another solar system.
Yeah, I would rather do that too.
Then push the Earth.
Yeah. You've already cut the humanity in half. Why don't you just cut it to
0?
or 100 people or something. It just seems absurd, but fascinating.
Definitely.
Were we talking about the thing that if Earth was moving, or maybe I read it somewhere else, if Earth was moving fast enough and hit Jupiter, what would happen? I think they said it would be like smashing even though Earth is so small, if it was moving fast enough, it could blow up Jupiter.
Wow. Huh. Yeah,
but
I guess it would be like
all the people would die, but I mean.
Yeah, it would be like an extreme asteroid impact.
Mm-hmm.
I still think Jupiter, yeah, I guess depends how fast we're talking. You know, is it an appreciable fraction of the speed of light?
Mhm.
If then, yeah, you could probably cause some huge damage to Jupiter.
Well, in the movie, it didn't look like Jupiter was very damaged by exploding with Earth's oxygen, you know?
Mhm.
I'm just being
Oxygen, right.
facetious.
Right, but I mean, that
And-
would all be gone on the surface.
As you could see the train of
There's-
atmosphere, of Earth's atmosphere as it was traveling.
Right.
So what, I mean, whatever.
Right. It's
Hmm.
So Ryan, I hope we're almost at 7. I hope you come back and do more. These have been great.
Thank you so much.
Yes, totally. You've done a really great job of discussing concepts that have been brought up by all these movies. Yeah,
I appreciate
that's been
that.
really, yeah, it's really great. I mean, you have so done your homework
Mhm.
and thoughtfulness about watching.
Yeah, and you also
gleaning
have
the
a,
essence.
and you have a good,
Yeah,
you have a foundation on many different levels. of
yeah,
knowledge. So it really
yeah.
makes this fascinating.
it's blown me away, and I've only done this 3 times, twice.
Mhm.
You've blown me away. So sorry to have you go when I'm just getting started,
Yeah,
but best of luck. And
yeah,
what an experience.
Thank
yeah.
you. Yeah, I had a great time doing these for sure.
Great.
Well, good luck. Stay in touch in some level, and I'm sure our paths will cross again.
Absolutely.
Yeah,
All right.
absolutely. All right.
Be well.
Toodaloo, all the best.
Thank you.
And
You guys
too.
enjoy.
All right, wait a minute. We'll do a visual. Bye.
Bye.